In this clip, we're going to finish the last few slides at the end of lecture 2. So in the lecture, due to disruption in the first lecture, we're kind of like an hour to 30 minutes to an hour behind. So I didn't get a chance to go into the concept of the lag operator and stationarity in more general ARP models in enough detail. So this clip is going to serve as the end of lecture 2, and also it's going to relate to the first question in exercise 1. So these two things together then, along with the podcast, will serve as the whole of lecture 2, such that in lecture 3 and 4 we can move on to estimation as originally planned, so that we don't keep getting behind, so I can explain the concept in estimation in proper detail. Okay, so in lecture then we gave the definition of the lag operator. The lag operator L satisfies this condition here. It just says that L of yt gives us yt minus 1. So performing the operation L on yt just lags back one period, the time series variable yt, to yt minus 1. Okay, so again, L here isn't a function, it's not a polynomial, it's not L times yt, it's not a function of yt, it just says L performs the operation on yt, it gives us back yt minus 1. Okay? And just to be clear, L is an operator, which is a different mathematical object to a function or a polynomial. Okay? We can, again, apply the lag operator more than once. So LL means apply the lag operator twice. We take the lag of yt, then we take the lag of this. Okay? By definition, L of yt equals yt minus 1. Okay? Then we have to form the L again, gives us L of yt minus 1. And again, by definition, the L lags back the variable one period. So one period back from t minus 1 gives us yt minus 2. Okay? Which we write shorthand that L squared of yt equals yt minus 2. So just to be clear then, we write as shorthand L squared equals LL. But L isn't a function. L squared is not L times L. It just means perform the lag operation twice. So this is just shorthand notation. So just to be clear, we're not multiplying L by L. We're writing this as shorthand notation. Okay? So in general then, if we have L of yt, we perform the lag 3 times such that we'd end up with yt minus 3. We write this shorthand as L cubed. More generally then, L to the j would mean perform the lag j times. It's going to give us yt minus j. Okay? So the benefit of the lag operator then is it allows us to write these ARMA models in what we call their lag operator form. It allows us to write very general models in a very succinct way. To give a simple example, take the AR1, which by definition, yt equals mu plus psi1 yt minus 1 plus epsilon t. And again, we can rewrite this using the lag operator as, well, this just is L of yt. By definition, L of yt gives us yt minus 1. Okay, we can just take this over here to the left-hand side, and we're going to get yt minus psi1 L of yt equals mu plus epsilon t, which we can then write as 1 minus psi1 L of yt equals mu plus epsilon t. So this here is what's known as the lag operator form of the AR1. It's equivalent to the AR1 model. Okay? And this using this lag operator becomes very beneficial, especially for the AR2 or general ARP models. It allows us to write it in a very succinct form. Okay? And it turns out there's a property of the lag operator which allows us to study the properties of more complex systems in a very simple form. Okay? And it turns out that this operator, although we're not multiplying the two things together, it still turns out that this operator L behaves like it's a polynomial. And to make this clear, I'm going to give an example. I'm now going to show that performing two operations on yt, two different operations. We have this operation on yt, and we have this operation on yt. These two things are equal to each other. Okay? And what do we note here about the operations we performed? Well, we can see that although this here isn't a polynomial L, and this isn't a polynomial in L in here, what we've seen is, we're going to show the two things are equal. We can see that 1 plus L of 1 minus L, if L were a polynomial, we can expand this out and we'd get 1 minus L squared. Okay? So what I'm saying is here, this here performs an operation on yt, and this here performs an operation on yt as well. And the two things turn out to be equal. So it just behaved as if this 1 plus L, 1 minus L, it behaved as if we could expand it out and treat it like a polynomial. Okay? So it still behaved. So what I mean by that is when we perform some operations on yt, we can still treat this. We can use all the usual manipulations of algebraic manipulations to rewrite this, and the properties remain. Okay? So let's show then that these two entities are equal to each other. Okay? Well, we've seen the part above gives us 1 minus L of yt. We'll expand this out. We're going to get yt minus L of yt, which by definition is going to give us yt minus 1. So we can see that the operation 1 minus L of yt just gives us the difference in yt. We're now going to perform the operation 1 plus L, 1 minus L of yt. Okay, well we just derived this above. It's here, the change in yt. So now we can just perform 1 plus L of this. Okay, and again expand it out, we're going to get yt minus 1 plus L at the lag of this. And by definition, we can expand out, we're going to get L of yt minus L yt minus 1 is just equal to lagging back yt 1 period, and we're going to lag back yt minus 1 period. So we're going to get this term here. And then, these two yt minus 1 cancel out, we're going to get yt minus 2. Okay? We're now going to show that 1 minus L squared of yt also gives us the exact same. Well, it's very simple. Expand out, we're going to get yt minus L squared yt, which again, L squared yt just means lag yt twice. We're going to get yt minus 2. So these two things are clearly equal to each other, which means that these two operations, these two entities are the same. All this and all this. So as we've seen then, this is what we've just shown here, these two things are exactly equal to each other, yt minus 2, which just means then that we could have got from here to here, we can just treat L like it's a polynomial. We can just expand, it still behaves as if 1 minus L, 1 plus L equals 1 minus L squared. Okay? So this is a very useful result then, because it means when we've got a process in its lag operator form, we can manipulate these functions in L and treat them like a polynomial, and all the properties remain the same. Okay? And this is the general result. So we're now going to use this result to write the AR1 in its MA infinity form, which we did in lectures. Okay, so remember this entity here, when we've shown before, this is just the AR1 model. Okay. And again, remember in lectures, we derived the MA infinity form by back substituting yt minus 1 again and again and again. And we wrote this process, under the restriction that the AR1 coefficient is less than 1 in absolute value. We kept recursing back and back and back. And we wrote this, remember, as an infinite lag of all sigma past lags of epsilon j. And we derived the AR1 coefficients. So we derived this in lecture. So what I'm going to show you now is we can use this key property of the lag operator form to use the lag operator representation of the AR1 to put it into its MA infinity form. Okay? So again, remember, 1 minus psi1 of L of yt is not what this multiplied by yt, it's performing an operation. But we've seen that this lag operator behaves as if it were a polynomial. So we can just divide both sides by 1 minus psi1 to the L. So these two things are equivalent to each other. Okay? And again, L behaves like a polynomial, so we can expand out the polynomial. We can expand this out. We're going to get two terms A and B. Okay? And what we're going to show is, this should be mu minus psi1. Okay? What we're going to show is that we're going to get the exact same MA infinity representation as we got in lecture, which we should expect to find because we know these two things have to be equal to each other. So we should get the exact same result. Okay? And again, L behaves like it's a polynomial. So this here is just a geometric progression in phi1 of L. So remember, for a geometric progression, 1 plus x squared plus x cubed plus dot 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 is equal to 1 over 1 minus x, i.e., it's 1 minus x to the minus 1, if x is less than 1 in absolute value. Okay, we now have a geometric progression in phi1 L. Okay, and again, L isn't a polynomial, but it behaves like one. And again, we're going to be working on the assumption that phi1 is less than 1. So again, because L behaves like a polynomial, we can show that this entity here is equal to this. It's a geometric progression in phi1 L. Okay, so we can now use this result to work out terms A and B. So working out term A then will again multiply out. We can use the result from here. We're going to get this term here. Expanding all through, and we can see that the lag of mu just equals mu, because mu is a constant. So lagging it back one period is just mu. L squared of mu just equals mu. Again, lagging back mu 2 period, it's still mu, because mu is always mu in every time period, and so on. L cubed mu equals mu, such that this simplifies down to here. Well, this here is just a geometric progression in phi1. So we're going to get, we take the mu outside, we're going to get this term here. Okay? So again, we're just using the result here that 1 plus phi1 squared plus dot 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 is equal to 1 over 1 minus phi1, when obviously phi1 is less than 1 in absolute value. Okay, so we've shown the first part. Okay, we've derived part A. We're now going to derive part B and show that we're going to get this term here, which we derived in lectures. Again, using this result here, multiplying out, treating L like it's a polynomial, going down from here to here, expanding through, and again, by definition, L epsilon t equals epsilon t last period. L squared epsilon t, again by definition, is epsilon t 2 periods back, and L cubed of epsilon t is equal to epsilon t 3 periods back. So then we can move from this line to here. Well, what do we have here? Well, it's literally just this sum here. Expanding this out at j equals 0, we're going to get phi1 to the 0, which is just 1, of epsilon t minus 0, plus phi1 epsilon t minus 1, plus phi1 squared epsilon t minus 2, plus dot dot dot, which is exactly the above here. So this just writes this in its sum form. Okay, so what we've shown is then we've derived the MA infinity representation of a stationary AR1, i.e. under the condition phi1 is less than 1. So we derived this in lectures by back substituting. We kept substituting in yt minus 1, then yt minus 2, and go back and back and back. And so long as phi1 is less than 1, the effect of the past eventually dies away, and we get this sum here. So we're doing the exact same thing. We're just showing now how we can use this lag operator form to express an AR1 in its MA infinity form. Okay, and this method is actually quicker than the recursing back and back and back. Okay, so we can see it's actually quite a powerful method. So again, treating L as if it was a polynomial, we divided both sides by this to get to here. These two things are equal to each other. This is just the AR1, and we're showing it's equivalent to this term here, treating L as if it was a polynomial. And this here is a general result. You don't need to be able to prove that L behaves as if it satisfies the usual algebraic laws, i.e. we can multiply and divide, etc., and use results like the geometric progression. You don't need to be able to prove this, but you need to be able to know that we can use this result, and you can see, we gave an example in the slide before, how, remember this example, we showed that these two entities were equal to each other, which meant that these two behaved as if they were a polynomial. We get you by this result here. Okay, so we've given a simple example. We gave another example where showing that treating L as a polynomial to get the MA infinity. Okay, so we're going to use this result. So again, this is a key result. So you need to know the result that we can treat L as if it were a polynomial, and we can use then this lag operator variable to derive the properties of more. It comes in handy for more complex AR type models. Okay, So we're now going to talk about stationarity of an AR2 process. Okay, so remember, we know for an AR1 process, we need, remember, for an AR1, the key condition is that psi1 is less than 1. Okay, we're now going to see, well, if we're now moving to an AR2, a more general case, we're now going to see, well, what are the restrictions on these AR1 coefficients, so AR2 coefficients, such that this process is stationary. Okay? And the simplest way to see what the restrictions must be, we're going to write the AR2 in its lag operator form. Well, yt minus 1 is just the lag of yt, and yt minus 2 is just the 2 lags of yt, which we write L squared. Okay, we can take these terms to the left-hand side. We then get the lag operator form of the AR2 model. Okay, well, we can now use the result from before that this term here behaves as if it were a polynomial. We can use all the algebraic law to re-express it in another form. Okay, so we can treat this as a quadratic in L and factor it just like we'd factor any quadratic function. Okay, so from now on we can, although as I kept saying, L isn't a polynomial, it's an operator, it still behaves, it still retains its properties as if it was a polynomial. So from now on, when we're doing this, we can think of L as a polynomial, and from here on in, we're just factoring a quadratic. All this says here is for any coefficients psi1 and psi2, we can always find these roots, lambda 1 and lambda 2, to express both sides of this. So we're just literally factoring the quadratic here. So again, this is basic algebraic results. We know that we can always find these roots. I'm going to give an example, especially in class 1, in the exercise class 1, we're going to give some examples of this. So that, using the result from before, we can re-express the AR2 in this form here, because the two things behave like each other, okay, which is because we factored the quadratic here. Okay, so we've now expressed the AR2 in this form here. And it turns out for stationarity, we need both of these roots to be less than 1 in absolute value. Okay, and why is that the case? Well, if either root was 1 or higher, the process would be explosive. So just take the case, just for example, that lambda 2 equaled 1. Okay, where lambda 1 could take any value. Again, it could, just to give an example, fix the case where just one of the roots is 1. Well, in that case, the AR2 looks like this. And again, L behaves like it's a polynomial. So we can divide both sides by 1 minus L, which is what we do here. And again, we can now expand out. We've divided both sides by 1 minus L. And again, this is a geometric progression in L. So we're going to get 1 plus L squared dot dot dot. So again, going from here to here. And then we can expand out. And we can see we're going to get this term here. Because remember, L of mu equals mu, L squared of mu equals mu. So we're just going to get the sum of mu plus mu plus mu plus mu an infinite number of times, so we're going to get infinity. Okay, this would hold if lambda 1 was equal to 1. Okay, sorry, so this should be lambda 1 here, but again, okay, that would be lambda 1. Okay? And again, we get the same result. If they were greater than 1, it would be explosive as well. So we need that both of them have to be less than 1. Otherwise, we're going to get an explosive series. Exactly as what we would found for the AR1 process. Okay? So you can see, using this lag operator form, re-expressing it in this way, we can see that both of these roots have to be less than 1 in absolute value. Otherwise, the process is going to be explosive. Okay? So then, how does this relate to the condition that I gave in the lecture? Remember, on one of the slides, we saw that an AR process, an ARP process, is stationary if the roots of the characteristic equation, which was defined in lectures, lie within the unit circle. So let's give the specific case for p equals 2. Okay, so for this case, this would be the characteristic function here. Result, the AR2 is stationary if the roots of this equation, i.e. the 2 vi's of lambda, again these are just the AR2 coefficients, if the roots of this equation i.e. the two values of lambda which solve this, again it's just a quadratic in lambda, if they're both less than 1 in absolute value, then the AR2 is stationary. And why is this? Well, it turns out that the roots of this equation are just exactly the roots as what we found before when we went from here to here. Okay, so when we gave the general result that for any phi1 and phi2 we can always factorize this for some roots, we're going to show that finding the roots of this characteristic equation, this here, turn out to be the same. Okay, so again, this is from the last slide. We can always factor this into this term here for some roots lambda 1 and lambda 2. So why are the roots of this equal to the roots here? Well, just divide, again, but this behaves like it's a polynomial in L. So just divide both sides by L squared. Okay, we're going to get L to the minus 2 minus phi1 L to the minus 1 minus phi2. And again, we're going to get divide by L and divide by L. So we're going to get to this here. Okay, because dividing this by L squared. So again, we're going to get divide by L squared, which we can just divide by L, divide by L. We're going to get to here. Okay, and again, well, what's this? This is just a polynomial in L to the minus 1. So just define L to the minus 1 as lambda, again, because L, this behaves like it's a polynomial in L. Well, re-expressing this, we've just got the characteristic equation here. Remember the characteristic equation from above. Okay, so we've seen then, so these two things are equal, defining lambda equals L to the minus 1, and these are exactly the roots from before. So again, lambda 1 and lambda 2 set this characteristic equation equal to naught, and these are the exact same roots which gave us the factorization in the quadratic above. And we saw that both of these roots had to be less than 1 in absolute value, otherwise the process would be explosive, exactly the same as it was for the AR1 type model. Which is why we can, for any AR process, just construct this characteristic equation, find the roots, and if they're less than 1 in absolute value, the process is stationary. Okay? And again, this is the definition of the characteristic function of an AR2. So this here just states the result. Any AR2 stationary, given any coefficients, construct this characteristic function lambda, find the roots. If they're both less than 1 in absolute value, the process is stationary. The reason being, both these roots have to be less than 1, otherwise the process is explosive. It means infinite mean, infinite variance, in which case it couldn't be stationary. Okay? And this result generalizes the general ARP. Okay, so it should be epsilon t here. Again, we can construct the characteristic function of an ARP. It's exactly the same form as before. Now we've got now p coefficients. And again, this will have p roots, and this ARP process will be stationary if the roots of this characteristic function are all less than 1 in absolute value. Because all it takes is any one of these roots to be 1 or greater than 1, and the process will be explosive. And we can see for p equals 2, we just get the special case of the characteristic function. For p equals 2, this is just lambda squared minus phi1 lambda of then minus phi2. Okay, but this is for the general result. Okay, so we've now then discussed the lag operator. We saw how we could express processes in their lag operator form. Okay, we wrote the AR1 and the AR2 in their lag operator form. And we saw that this lag operator has a very beneficial quality that we can manipulate L, we can re-express functions of L as if they behave like a polynomial. When we perform this operation on y, they still retain all their properties as if we can multiply and divide by L, even though technically speaking it's not a polynomial, as I've repeated now numerous times. Okay. From there then, we saw how we could express more complex systems in their lag operator form and use this property then to see when a process is going to be stationary, and we did that for an AR2. Okay, and we gave the general condition when an AR2 is going to be stationary, which is this here, and then generalizing then for general P, this is the general result. Okay, and again, you don't need to be able to kind of prove formally why these two conditions will give stationarity, but you can see the intuition by the example before that if any of these roots weren't less than 1 in absolute value, the process would be explosive. Okay, so that now is the end of the discussion on the lag operator and stationarity in AR2 models. The first question in class 1 is going to be asking you to verify whether particular AR2 processes are stationary, and you're going to use this result. Okay, so in the class on Tuesday, I'm going to re-express some of the ideas I've talked about in this video again. So again, it's useful if you can, maybe if you didn't follow some of the ideas, to listen to the video again, and if you have any questions about anything I said in the video, you can bring them up in the class on Tuesday. Okay, so this now is the end of lecture 2, such that in lecture 3 we can move on to estimation and model selection, which is the second half, of my half of the course. Okay.